Okay, so hello everyone, I'm Davide Mainardi from the Italian team, and I'm going to show you our solution to the problem number 1, rail track divination. First of all, the problem said that the sound of an approaching train propagating in metals reaches our ears earlier than the train arrives. So it asks if it is possible to estimate the distance and the velocity of the train in movement using this phenomenon. The problem asks also to estimate the accuracy and precision of our method. I want to remark that this problem asks only to find a theoretical model, and we were not supposed to do any experiment. First of all, we are going to investigate which is the sounds of the train origin, and then to analyze this phenomenon and to implement a method to determine the velocity and the distance of the train, and then we will do a little recap. So, which is the origin of the sound of the train? Well, when the wheel of the train rotates on the rail, because of the corrugations of the rail, the wheel goes up and down, and it also stretches the rail. So this stretchment produces a vibration into the rail, and we're going to use this phenomenon to investigate, to estimate the velocity and the distance of the train. So we can see an image, a picture, and we can see that the rail corrugation generates frequency at the frequency of about 10 to the 4th power. So it's in the hearable range, we can hear that, and we will use this type of vibrations. Now, let's analyze this phenomenon. This is a simulation of the propagation of these longitudinal waves into the rail, and we can see, maybe in this picture it is not very clear, but we can see that the density of the points changes in going along the x-axis. So this is a longitudinal wave, and we know the equation of the propagation of a wave in a solid, and we can estimate the velocity knowing the Young's modulus and the density of the material which is composed the rail. So, if we are far from the source, so from the train, we don't have a forsating constant, so which is the F term in this equation, and so we can find the general solution of the propagation of the wave into the material. And what is important is that the Young's modulus doesn't change a lot with temperature, because okay, this picture is not very clear because it shows temperature from. It doesn't show temperature in the range of 0 to 50 degrees, which is the region we are interested in. But that's what we find, and we think that in the maximum inclination of the curve is some way small, so we can estimate quite better that the Young's modulus in this region will have a value between 200 and 220 gigapascal, so we can estimate the velocity of the propagation of the wave into the rail. Now, we we found an article which shows clearly that the rail acts as a bandpass filter for frequencies, and we are interested in these frequencies that are the frequencies of the longitudinal wave that was produced by the wheel and the corrugations. So we can think that the attenuation of these waves through the rail is small, and we can use these frequencies to analyze the phenomenon. So, how we think we can set up a method to estimate the velocity of the train and to estimate its distance from us. First of all, we thought that we can use some accelerometer that we can put on the rail, and we put this accelerometer at a certain distance, not too big, because otherwise we can make an accelerometer very far from us, and we can say, okay, the train is there. It's not the request. So if in a range between 1 to 10 meters would be the distance of two accelerometer. Well, when the train arrives, it produces, when it is far from us, it produces a wave. So we can use the accelerometer to measure the intensity of this wave. At a certain time, the amplitude of the wave reaches a certain amplitude that makes open a trigger in the first accelerometer. Then, after a time of the distance between the accelerometer in A and the accelerometer in B, divided by the velocity of the wave into the material, we do a second measurement with the second accelerometer. So we can estimate the velocity of the train, because we know that we can estimate the attenuation of the wave into the material, and it's crucial for the estimation of the distance. But what is important for the estimation of the velocity is that when it opens the trigger in A, we measure a certain amplitude, and when the wave reaches the same amplitude in the second accelerometer, we know that the train covered that distance, because the point of generation of the wave is the same distance in T1 in A and the same distance of T2 in B. So, but how about the distance? It is pretty difficult to estimate the distance, because we should know the amplitude of the oscillation produced by the train. And knowing the attenuation of the rail, we could estimate the distance, but what's important is that we should know the amplitude of the wave near the train, and it could be influenced by a lot of parameters, like the type of material of the rail, or the material of the wheel, the dimension of the wheel, and so it's very difficult to estimate distance. We should know the characteristic of the train which is approaching to do that, I think. So, now our conclusions. So, we understood that the noise is caused by the contact between the corrugation and the wheel of the train. Then we set up a possible, we explained a possible setup to measure the distance and speed of the train, and we know the parameters to estimate the distance, the velocity, but not the distance, because it depends on the train's properties.
Okay, thank you.
So thank you for your presentation. First of all, okay, so this is the problem statement. It asks us, is it possible to estimate the distance to the train and speed of its moving using, okay, it states it reaches our ears earlier than the train. So, I will get to this later, but let me just say something about the presentation itself. It was a very simple and elegant presentation. It was easy to follow, I must say that. It was okay model of the waves and reason why waves emerge in the first place. So I like that. They pointed out the filter mechanism of the rail track, that it acts as a bandpass filter, and they showed the graph of it. And they made an attempt at a hypothetical experimental setup. But, of course, the large concern is there is absolutely no experiment. And I know they stated, the reporter stated that it isn't required by the problem statement, but I'm not sure why it wouldn't be required by the problem statement. So I think it is, of course, it's necessary to check if the method you developed is applicable in practice. So yes, I'm not sure why you think it is okay to not have any experiment. And of course, without the experiment, you don't have any reference of accuracy or the precision of the model. So I think that's the big part of the task. And I will just let me just get back to the ear thing. Of course, it is not, in my opinion, required to listen to the sound with ears. It makes no sense. But it is, as a human, you have two ears which are separated by distance of around 10 centimeters. Okay, but you use two microphones or accelerometers. They are far apart, probably much more than 10 centimeters. So this, in principle, this your mechanism couldn't be done with just one microphone, which is in reality what a person would hear, right? And also there are some things I would like to talk about. So let me just go here. So is the signal periodic or random? So I don't know. I don't know if you measured the actual sound of the wave. Have you tried? But it isn't a sine wave with some frequency and attenuation. So it's if you ever rode the train, and I guess you have, you know it has bumps and it has this area you can feel it skipping a bit and making a sound, and these bumps are very noticeable in the signal itself that you hear in the tracks. It is not a pure sine, of course. Different trains or rail tracks. Your model is limited to one train and one rail track. Also, geometry of trains does the curvature of that specific train track influence how it will attenuate through the track, and attenuation from track holders. If you see the picture of a track, it has every 10 meters the track holders by its side, which transfer the energy to the ground of vibration. So I would first ask you, did you maybe, or do you know how the signal you would get from accelerometer would look like. And what type of accelerometer would you construct?
Okay, we proceed to the discussion.
Okay, obviously the signal is not periodic, but what is important is that with two accelerometers, when we get the same signal in the second accelerometer and what we saw in the first one, we know that that is the signal from the train.
Okay, that I would.
It's just
okay, but
attenuated.
okay, but how would you first? How would you make your accelerometer?
Okay, I showed a picture where we can.
Yes, of course.
Okay. When I showed the accelerometer, which is made with a piezoelectric.
Okay, piezoelectric. Nice, thank you.
Okay.
But what you said, I have a small remark. So you have not all frequencies in metal travel at the same speed. Okay, you have wave dispersion.
Okay.
So if you have this wave at the point x where you measured, it will disperse more at the x plus delta x. So you wouldn't actually measure the same wave at the point that was further away.
Okay.
It would
I think if
it be a different shape. So
okay, honestly, we didn't any measurement as I said, because okay, I have to make a remark. It is not expressly asked to make measurements.
but
It could be
yeah,
done,
I think
but
it is
we
implied,
didn't because it is very difficult to do that and also to reproduce it in a laboratory because of the dimensions of a train.
So
This if we put accelerometers as a relatively small distance, I think this phenomenon hasn't a very big effect.
Okay, so let's just okay, but can you give me an estimate of the order of magnitude that you would need this delta x to be to make your method value?
Well, it depends on the accelerometer you
Yeah,
use.
of course, but can you give me order of magnitude with real accelerometers that you could make?
Honestly, I don't know.
So you don't know if this method could be applied?
Yes, it could be applied. The limitation in the accelerometer is that we can know the distance, the velocity when the train is at a certain distance. If the train is very far from us, the attenuation through the rail doesn't allow us to know the velocity. But if it is, we are there, the train is there, obviously we are able to do that.
Okay, but so let me just ask one thing. How would you mount the accelerometer on the train track?
Well, it's,
On the side, right?
yes.
But you said the trains, the waves in the track are longitudinal. So you would expect the accelerometer to measure those longitudinal waves in the track.
Yes.
Like it would move parallel to the track,
Yes.
not like this.
No. Yeah, if we are on the track of the rail, this is a top view. The train, what does the rail is that it moves this way.
This is a top view,
Yes.
and you would place the accelerometer like somewhere on the
Yes.
side here, and it would do this.
Yes.
This seems okay to you. Okay. Okay, I think it's very, very, very difficult to make the accelerometer of adequate precision to try to pick up this kind of movement, which is longitudinal.
Okay.
Do you know maybe what are the amplitudes that you would expect here of the movement?
Maybe some 0.5 millimeters.
0.5 millimeters. So if I put
It depends on the distance of the train. the limitation of our method is that we are not able to know the velocity of the train if it is very distant for us.
So overall, both teams presented some really interesting points. This is a very challenging problem because it involves a lot of things that are difficult to experiment on. Railway divination is all about trying to find the position and velocity of a train running along a track. And to do that requires a lot of investigation into the materials that a track is made with, and then also how vibrations are produced by the train and how they propagate along the track. I very much enjoyed the reporter's speech. I thought his investigation of the theoretical models and the actual physical parameters behind those was very interesting, particularly the bulk modulus, including the bulk modulus to find the change in the velocity of wave propagation through the track, I thought was very important because each track material will have a different wave propagation velocity. I also thought considering other relevant parameters, such as the different kinds of vibration that could be produced by a train, was quite important, and that was a point that the opponent quite clearly stated, and that was excellent. I thought, on the other hand as well, in terms of the reporter's presentation, it would have been great to have an experiment to verify some of the physical parameters that were occurring within the experiment. Within the theoretical model. So having the ability to deduce, okay, if we were to change a specific physical parameter of the track, for example, or the track length, or the vibration propagation, how might that affect the signal that we detect? And is the theoretical experiment that the reporter proposed one that is feasible in real-world scenarios? For developing a model with, so the second half of the question focused on developing a model for the distance, so working out the displacement of the train on the track at any particular time. I thought it would have been great to be able to develop that further and to have more of a discussion. So I think that spending the next few minutes discussing how to develop a model for the distance of the train would be excellent. And then it would have been great to support the model with numerical values, but that's something else that we can discuss. From the opponent, it was great that you pointed out some of the other physical parameters, such as the different kinds of vibration, as I said earlier. So for the discussion that we will be having soon, it would be great to discuss if you considered another physical parameter, such as track deformation, so the movement of the track as the train passes over it, as a source of vibration, rather than just the wheels moving on the track as the primary source of vibration. Also, if we considered things like soil damping, and then on the train, there are many different parts that produce vibration, and that was one of the graphs that you had. There were different sources of vibration if you considered those in your model, and then how might they affect your model. And then is there a type of sensor that would be best suited to doing a proper experiment, as you mentioned earlier? So, yeah.
So we can proceed to discussion.
Yes, so if we wanted to start with the main point about track deformation as being a potential source of the primary vibration.
We feel that track deformation, and specifically it produces much more distinctive and easy to detect sounds than the waves that you were speaking of.
Okay, the main problem is that, as is stated in this slide, we can show that some frequencies are cut off by the rail because it acts at a bandpass filter. So you, at a long distance, you can work with this type of frequencies.
This is true, but there are two effects here. The greater cutoff rate helps us reduce this delta X you were talking about. So of course we sacrifice some distance. We sacrifice maximum distance. We can hear the train, but we can limit the
other type of
so
waves.
there's a balance.
That could be good, but the method I showed you could be also used with other frequencies. Is not vinculated to the use of these frequencies. It is an example because they are the frequency that works better for our purpose, because we can estimate the velocity of a very far train. If the train is at
So if we could move on in our discussion, is there a particular way that you might be able to consolidate or improve your model to work more on the distance that the train is traveling?
Well, with our model, to know the distance of the train, you need to know the characteristic of the train. Maybe the dimension of the wheel is the same for the trains. We know the parameters of the rail. The weight of the train.
Would we be able to?
Yes,
I agree with you, but do you think that this is also this characteristic you speak of is also a function of the velocity of the train?
Well, yes.
No. You said you need to know the specifics of the train,
Okay.
but I'm asking, is that enough? Do you need to know the velocity of the train also?
Okay,
Because
the
then-
velocity of the train affects the amplitude of the waves, because obviously if we have some.
Yes, but then
Some-
how can you tell the distance?
Sorry.
So you know.
With the first method, we can know the velocity of the train. Okay, so we can also estimate this parameter.
Okay. So you will measure the velocity first, and then use
Yes,
those
obviously,
measured velocity to calculate the distance.
Would we be able to
It
move
is
this
a
discussion on a
possible-
bit? Just
Yeah.
looking at another parameter, if we had only one sensor, would it be possible to measure the same physical characteristics and get the same data that we need?
I think yes, because you don't need actual two sensors. You can look at the derivation in one sensor. In my opinion, you can look at the time evolution, derivation of the curve
Okay.
in one sensor. That gives you the similar
Signal in
signal as if you had two that are spaced apart. You can just look at the time spacing and not the distance spacing.
How we introduce the teams?
Okay, does any team have a question they would like to ask? Yes?
Just a technical question. You said that you didn't do the experiments because you cannot reproduce it in laboratory.
Well,
Well, why didn't you go to the rail track?
technically, first of all, it's a bit. No, it's not very dangerous, but I can go into a rail and put then some accelerometers. If I think it's also illegal.
Do you think it would be possible perhaps to scale an experiment down to a lab size? So perhaps
Well,
look
it
at
is
the-
possible, but it changes a lot of parameters because the train is very big. We can't reproduce it in a laboratory.
But
So
I think the toy model could be better than no experiment at all. Maybe.
yes, maybe it would be better.
Do you have a justification for how that might be able to improve the model perhaps?
Yeah, I think they would find that it is extremely hard to do it in the way they proposed.
Okay.
Okay,
Does
but-
any other team have a question that they would like to propose for this problem? Okay, so
Okay, I think you can reproduce it in a lab, but there are a lot of variables that changes between a laboratory experiment and a real rail track. Okay, it's good to
there's a
do some
question
experiments.
over here. Yes?
Can you estimate the accuracy and the precision of your method?
Well, as I said, the accuracy of the method depends on the.
Theoretical, you have a theoretical model which predicts something. Accuracy and precision. What is it?
I can say on what depends the accuracy, but not estimate properly the accuracy.
Okay.
Do either the reporter or the reporter or the opponent have a perspective on how soil damping might affect the model and how, in a real-world scenario, that might impact the vibration propagation?
Soil damping, of course, limits the distance from which we can observe the train, and also it also has its own filter of frequencies, which are different than those of the tracks itself.
Okay. Were there any other questions from the floor that? Yes?
Would there potentially be any other types of sensors other than accelerometers to make any measurements? That's the question from the reporter. any other kind of electrical sensors that you could?
Yes, we can use, for example, some lasers to know the position of the rail.
Is there? I noticed before you were discussing with piezoelectrics and accelerometers. Would there be a benefit of using one or the other?
We didn't thought about that.
Okay.
So,
Does the opponent have a comment?
Well, I don't know what to
Okay. Are there any other questions that would like to be asked? We've still got some time.
And maybe looking at the actual sound, and because the sound is stated in the problem, and not, I know it's...
okay, it is asked to use this phenomenon, so we thought that the phenomenon is the...
Why do you think it's much better to use piezoelectric than the microphone, for example?
Because we can estimate the distance also of a very far train. The sound is
There's a question.
could be
Let me finish all.
okay. We can also use microphones. We think as a small sensitivity compared to an accelerometer, so it's better to use an accelerometer than microphones.
So I think it's a
I
sensitivity
just
thing,
want
okay.
to say, yeah, you cannot hear it by your ears because your ear has 0 decibel range, but with good microphone you could potentially hear it better. For instance, sensitivity of -40 decibels or something. So it's not heard by ear, but you heard by a good
But
microphone.
I think your choice was justified, because if you use microphone, you pick up a lot of noise from the that you don't want to pick up from nearby church, from
Yes,
birds
also.
chipping or whatever. And I think the
Yes,
piezo-
you can put a bandpass filter on the
yeah,
microphone.
you
so-
can, but it is a very
Yes.
To move the
So
topic
I
of
understood
discussion.
it. The time is out.
The position stated out that the position you wanted to put the accelerometer is not good to measure longitudinal weight. Do you have a way to improve your setup in order to measure it?
Okay, we can put an iron. For example, if we put 2 accelerometers, one horizontally and one vertical, when one that can only vibrate horizontally and one only vertically.
Can you draw something? Because it's not clear why.
Okay. This is the piezoelectric material.
Yeah.
Okay. And if we have something on that, it vibrates in this direction. The main contribute to the
How is the rail? Yeah.
okay is just an this is the rail, and this is this one that pushes the piezoelectric material, and this is the piezoelectric material.
Does the opponent want to add something?
Yeah, I think it is much more practical to pick up the transversal waves.
No, but in order to pick up the longitudinal weight.
Okay, I think
Yeah.
for this question is enough. Let us move to other questions. Richard.
Yes, the reporters say that you cannot scale down the model because many things will change. And my question to the opponent is, why, if you scale down the model, will everything scale down? Or what will the problem, if any, you will have?
Well, we didn't actually scale it. We didn't actually scale it down. We did the.
No, not what you did. It's what you think.
Okay. What I think. Well. I don't think it would be ideal to scale it down.
But why? That's the question. But maybe the reviewer can add something.
I think scaling down the model does mean that the sensors that you have to use and the equipment that you have to use to actually find the relevant frequencies would need to be different, which means that it may be compromised in terms of producing a valid scaled down experiment. So you may not be able to get the data that you need.
Okay.
Yeah.
Okay. Any more questions, Mark?
Could you please clarify it once again, the slide with the simulation? What does the simulation do? What are the results of the simulation?
It is only a simulation that shows that our wave, the wave we are investigating is a longitudinal wave. So I think this is the meaning of the simulation.
Yeah.
Can I follow up? What are the black dots and what's going on in the vertical direction?
Sorry?
What are the black dots? What does a black dot mean?
It is the density of the material. So if the wave propagates through the material, what happens is that the rail changes, deformates itself. So this is what happened to the rail, and this is a pressure wave.
So every dot is a region of high pressure or low pressure? Or
If you have the rail relaxed, or the dots are are uniformly distributed, this is what happens when the train passes on the rail.
Okay. If no any more questions, let's us upload all the data.